Hello students, welcome to a live session with Time, and we are going to take up this coordination compounds as the topic, which is part of chemistry. So before we begin, I just want you to note our details of the channel, wherein you'll find interesting videos which are going to take up 11th and 12th topics at all levels, not only for the board, also for your entrances of various types. We have noted there JEE, NEET, CUET, PITSAT, and other related exams. Now, if you're all ready, we'll start now. So this topic, coordination compounds, belongs to inorganic chemistry. And within this, today's session will deal with all questions that have appeared in the entrance exams. So I think you will be finding this interesting because especially when you're in the 12th now and then you're writing your board exams, pre-board exams, and then awaiting the next month JEE main, right, and a battery of exams that follow. I thought it will be good that you will benefit when we take up questions. All right, so in this first question, from the magnetic behavior of NiCl4 2-, which is paramagnetic, and NiCO taken 4 times, which is diamagnetic, choose the correct geometry and the oxidation state. Now, these are all the options given. Now, we'll take up each such and then check. First of all, what is the oxidation state? That is very easy to find out. Chlorine is -1, so I'll do it here. So if nickel is X, there are 4 chlorines. Each chlorine will have -1, and that whole thing is equal to -2. So X is +2. So the oxidation state is clear. So oxidation state is +2 for NiCl4, which means that 4 is out. Clear? We cannot have 4 for nickel, which is giving oxidation state of 0. Next thing is in nickel carbon tetrachloride, that is, sorry, nickel tetracarbonyl. I'm sorry for that. This is carbon monoxide with 0 charge, and that entire complex is 0 charge. Therefore, nickel is also 0, which means that 1 cannot be correct. So 1 and 4 are out. Next, we need to look at the correct geometry. Now, let us look at what is the magnetic character of NiCl4 2-. It is paramagnetic. If it is paramagnetic, see, it is a tetra-coordinate complex. So it could be either tetrahedral or square planar. Now, how are the orbitals split? In tetrahedral, you will have an E down and a T2 up. And in a square planar, you have 2 degenerate, then the third one, then the fourth one, and the fifth one. So 5 d orbitals. Now in tetrahedral, we have nickel in +2 oxidation state. So nickel is D8. So arrange the D8 here. 1, 2, 3, 4, 5, 6, 7, and 8. Which means that this is paramagnetic. There are 2 unpaired electrons, right? In tetrahedral, we always go for what? Not pairing, because delta T is much less, so you will not do the pairing. In square planar, look at the D8, how it can be accommodated. 1, 2, 3, 4, 5, 6, 7, 8. So this is diamagnetic. So square planar is not possible. So square planar is out means 2 is also out. Therefore, 3 is the answer, right? Let us look at 3 tetrahedral. Yes, it is correct. Now, what about NiCO taken 4 times with nickel at 0 oxidation state? Now, how is this tetrahedral? Look at this. Nickel tetracarbonyl, yes, is having a D8 and S2 because there is 0 oxidation state. D8, 1, 2, 3, 4, 5, 6, 7, and 8. There are 2 unpaired electrons, and then a S2 configuration here. But then it is mentioned that it is diamagnetic, which means that these 2 electrons have entered the D and made all paired electrons. They're all now paired. So S is free. When the S is free, it can hybridize with the 3p to make tetrahedral. sp3 is nothing but tetrahedral, which is how we got Ni with 0 oxidation state in tetrahedral geometry, and for NiCl4 2 minus, Ni is in +2 state and it is tetrahedral. I hope this is clear. So the first thing that we did was we found out the oxidation state, which is the simplest one. So find out the oxidation state and look at the magnetic character. Magnetic character saw to it that square pennant is not allowed because square pennant gives a diamagnetic complex, whereas tetrahedral will give a paramagnetic. And then for nickel tetracarbonyl, we have got the S electrons getting into the D because there is diamagnetic character. There cannot be unpaired electrons. And CO, is a strong ligand. Is the strongest ligand in the series. And that will make sure that these two electrons enter the D and the S is free. Once the S is free, the 3 P's are also there. So that will give you sp3. sp3 means tetrahedral. I hope this is clear. So option is 3. Having done the first question, right? I hope you are in a better state now. We have compared 2 nickel 4 coordinate complexes. Clear? Next question. A reagent which gives brilliant red precipitate with nickel ions in basic medium is, this we know very well, is dimethyl dioxide, because this forms that NiDMG taken twice, which is a rose red precipitate, which is a verification for the presence of nickel. So nickel is in +2 oxidation state. Now, what happens here? Let us look at the structure. I think that will give us this is dimethyl dioxide. This on treatment with nickel 2+. We'll change the pen now. This is Ni2+, probably that is not appearing there. And then it is dull there. So the same Ni is here. Now this is the complex that we form. And you know that 2 H+ ions have come out. That is because the medium is basic. You could use NH4OH, sufficient to remove the H+. So this nickel 2+ is forming this complex, which is rose red in color, which is what is mentioned here, brilliant red. Now look at this. If you take nickel as atom number 1, this is 2, this is 3, 4, 5, and 6. So a 6-membered ring has been formed on either side. That is a very important thing that you notice in this NiDMG complex. So this is the 6-membered chelate. It's a chelate. Chelate means the ring has got closed, because though this is open, right? With nickel, you've got a closed chain of 6 atoms. So 6-membered chelate is formed when nickel forms a complex with DMG in the presence of a basic medium. I hope this is clear. So option is what? Option is 4. I think it was fairly easier one, because this you need to know. See, you may not know about the role of sodium nitroprusside or neutral FeCl3 or metadinitrobenzene, right? But then you know that DMG has a specific complex formed with nickel. Hope this is clear. Yes. Now shall we move on to the next question? Now this we have chosen from NEET 2025. So here and there, wherever I have found that this has appeared in the previous exam, I have made it a point to note the year also. So this is from NEET 2025. Out of the following complex compounds, which of the compounds will have the minimum conductance in solution? Conductance is because of what? Moving charge, which are ions. So when ions are less in number, we will have minimum conductance, correct? Now all that we need to do is find out which of these complexes in these options given are giving less ions. Now take the first one. First one will give 1 square bracket and 3 Cl minus ions. Square bracket will be 3 plus. So I'm writing it for the first one. So total ions are how many? 4 are there. B bit, the complex and 2 Cl minus. Complex will be 2 plus. And this will be how many? This will be 3. Third one, you have only the complex. There is no co-ion. There is no co-ion. The complex itself is uncharged. So you have only one complex, and that complex is also not charged. So all the conductance that you will get will come only from water, which is a medium, is it not? And the D bit is giving a square bracket and 1 Cl minus. So square bracket is 1 plus. So there are 2 ions. So the one which has not given any ions should have the minimum conductance. The conductance that will correspond to what? Just the water that is present. Clear? So this is option C. If you want to make an order, so I shall write C less than D less than B less than A. Is it not? The number of ions are increasing in that order. So D is less than B is less than A. Clear? I hope this is a simple question, right? All that we need to do is find out which one gives less ions in solution. You know that the square bracket and the outside ion will get split. That is a primary valency, ionizable, isn't it? Within the square bracket, you have got non-ionizable. There is a coordinate covalent bond. Here. Next, this has also appeared in NEET 2025. Which of the following are paramagnetic? This we have already seen in the first question, so I'm not going to repeat. There are 2 unpaired electrons, is it not? This is diamagnetic, so this is not to be included. This is a square planar complex, which will also be diamagnetic, just like how you saw in the previous split of the d orbitals. So Ni is in +2 oxidation state, so this is D8. So I will put the D8, 1, 2, 3, 4, 5, 6, 7, and 8. And then that will undergo DsP2 hybridization, which is for square planar complex. Now this is diamagnetic because there is no unpaired electrons. What about NiH2O taken 4 times? It is similar to Cl because Cl and H2 are weak field ligands. So it is a tetrahedral complex that is going to happen. So E is down, the T2 is up, and then we have got D8. So 1, 2, 3, 4, 5, 6, 7, and 8. So again 2 unpaired electrons. So this is also having 2 unpaired electrons. And you know that triphenylphosphine is a strong field ligand. So that will also make it diamagnetic. So A and D are the only ones which give a paramagnetic complex. Check the options. A and D only. So it is option A. I hope this is clear. So we need to know the spectrochemical series. So whenever we are dealing with a question, we'll also check what are all the necessary inputs for getting an answer for this question. So spectrochemical series will tell us which ligand is weak and which is a strong ligand, strong field ligand, weak field ligand. We need to know the spectrochemical series, right? CO, you know, is on top, means anything is less than CO. So like that, you have various ligands ordered up, right? And then we have a distinction between strong field ligand and a weak field ligand. And we know that triphenylphosphine is a strong field ligand. It will pair up the electrons and therefore you'll get a square planar instead of a tetrahedral. I hope this is clear. So option A it is. Next question, also taken from NEET 2025. Now, what is the correct order of wavelength of light absorbed by the following complexes? Now check what is the geometry. 6 ligands, octahedral, 6 ligands, 6 ligands, 6 ligands. So all are octahedral. In octahedral, what do we have? We have a T2G and an EG. So the d orbitals are split, right, when ligands approach. And these are the d orbitals which are not facing the ligands, and those are facing the ligands. What is the gap between them? That is nothing but the delta O. Now, what is actually happening? Why is the light being absorbed? The light is being absorbed because an electron from the T2G can get excited to EG. So how much is the energy gap? Delta O. So that should be equal to Hc by lambda. So this is the lambda that the question is asking about. Now, shall we say stronger the ligand, more the delta O, correct? because there is more split. And lesser the lambda, correct? This is what we need to take up. If the ligand is strong, the delta O is more and the lambda is less, because delta O and lambda are inversely related, isn't it? Now, the strongest ligand among these is CN. Therefore, B will be minimum, right? Minimum wavelength is for B. Okay, there are options. Good that I have not crossed the border. So minimum is for B, right? So minimum is for B means it cannot be C, it cannot be D, because everything should be greater than B. Now, what is the minimum here? Look at C and D, both are having H2O. But in C, there is 2 plus charge. The metal is having lesser charge. Wherever the charge is less, the delta O is less. Here the charge is more, therefore delta O is more. So delta O is more for D, less for C. So C should be the minimum delta O. So maximum lambda greater than D, D greater than A greater than B, because B is the strongest ligand, followed by ammonia, right? And then between the two C and D, both are having only water as a ligand. We have the metal with 2 plus, central metal is 2 plus in C, therefore that is having less split and therefore more lambda. So C is the maximum. So where is this? This option is in A. Clear? Option A gives the right order. I hope this is clear. Yes. So a question may come on wave number, which will be the opposite, because wave number is the inverse of lambda. Wave number is proportional to nu, proportional to delta O. Clear? So wave number, if you get a question, that will be the reverse now. Clear? Next question. 2 statements are given, taken from NEET 2024. Now let us change the pen for some difference. Both CONH3 taken 6 times 3 plus and COF6 3 minus complexes are octahedral. Yes, 6 ligands, therefore octahedral. So first part is clear, but differ in their magnetic behavior. Now you know that NH3 is a strong field ligand and fluorine is a weak field ligand. So what do we expect? Suppose we put the T2G and EG. For the first one I am putting, and for the second one, the gap is less. So this is the second one. For the weak field ligand, I am putting it here. So CO is in +3 oxidation state. +3 oxidation state means what? Cobalt is having a D6 configuration, because cobalt is D7S2. We need to remove 3 electrons. So when you remove 3 electrons, you're left with what? 2 S electrons are gone. 1 D is also gone. So it will be D6. Strong field ligand, the first one I'm putting it here. 1, 2, 3, and the pairing will happen 4, 5, and 6. So it is diamagnetic. I'll put it here itself. Diamagnetic, because there are no unpaired electrons. What about the second one? Fluoride is a weak field ligand. Again, cobalt is in +3 oxidation state. So again, it is D6. And how the D6 will be here? 1, 2, 3, 4, 5, and then 6. There are 4 unpaired electrons, so it is paramagnetic. So the first statement is true. Magnetic behavior is not the same for both. Both are octahedral, but one is showing a diamagnetic character, that is the one with strong field ligand, and the other one with a weak field ligand is showing a paramagnetic character. So magnetic character is different. Magnetic behavior is different. Therefore, statement 1 is true. What about the second statement? That is what you're saying. CONH3 taken 6 times 3 plus is diamagnetic, whereas COF6 3 minus is paramagnetic. That is what you said, which means that both the statements are true, correct? So both statement 1 and statement 2 are true. Let us check. Option D it is. Clear? So again, spectrochemical series will tell us which one of these ligands is strong and which is weak. And the one which is strong will create a delta O, right, so greater that it will be more than pairing. So pairing will happen. So whenever there is a strong field ligand, the delta O will be more. Therefore, it will be more than the pairing. So pairing will happen. And therefore, you will get less spin complex. Or we can say, let us put the simple word, less spin. And when delta O is less than P, which will happen for a weak field ligand, right, this will be more spin. So we'll write less spin and more spin in simple language, right? So this is what we need to check. So we found that here the gap is more. For strong field, the gap is more. Therefore, it has become diamagnetic because it has got paired up. Pairing up will give you diamagnetic character. And here when the pairing up has not happened, you get a paramagnetic character. So option is D. I hope this is clear. Yes. We'll move on to the next question. So these are all questions taken from NEET. Again, NEET 2024. The correct spin-only magnetic moment. What is a spin-only magnetic moment? Spin-only magnetic moment is given by how many unpaired electrons are there. As many unpaired electrons are there, suppose it is n in number, this will be the spin-only magnetic moment in Bohr magnetons. Now for this complex COF63 minus, you know that cobalt is in what oxidation state? So X minus 6 is equal to minus 3. So this is plus 3. Here C2O4 oxalate is 2 minus. 2 minus into 3 is 6 minus, and X minus 6 is equal to minus 3. So this is also plus 3. So both are plus 3 complexes. Let us look at the options. Now, the first one is a weak field ligand that we have seen already. And then the second one is a strong field ligand because C2O4 2 minus can form a chelate. Means it can encapsulate the metal. For example, suppose this is a metal. How will be the oxalate? O, CO, CO, O. And that will make a chelate with the metal. So the metal is having a ring formed with the C2O4 2 minus. Whenever chelation happens, there is a favorable, what shall we say, delta G with an entropy. So entropy is a factor that is responsible for stability of a chelated complex. A chelated complex is more stable because of a favorable entropy. So when the chelate forms, the number of particles on the right hand side will be more. More particles, more entropy. So there is an entropy favor. Means entropy is increasing as the chelate is being formed. Clear? So the chelate is formed. There is a favorable entropy, and we know that delta G is equal to delta H minus T delta S. When delta S is more positive, the delta G is going to be more negative. More negative means spontaneous process. Is it not that you have learned from thermodynamics? Is it not? Now, this weak field cobalt complex 1, 2, 3, 4, 5. D6 configuration will give you 1, 2, 3, 4, 5, 6. And for a strong field, what will be the D6? 1, 2, 3, 4, 5, 6. So it is being paired up. So here there is no unpaired electron. So N is equal to 0. Therefore, there is no spin-only magnetic moment. Whereas here it will be more than 4. So root of 4 into 4 plus 2 is what? 4 into 6, 24. So root of 24 is slightly less than 5 or 4 point something, 4.9. So option C should be okay. For the, sorry, it's the reverse. For the first one, weak field. Yeah, weak field it is correct. Less than 5. And the strong field is 0. Correct. So C is the option. Let us check. Correct. So we find that again the spectrochemical series has given us a chance of getting which one is paired up, which one is not paired up. And on this basis, we are able to find out how many unpaired electrons are there. And depending on the number of unpaired electrons, we have a formula, and that will give us the spin-only magnetic moment. Clear? So all these things are quite important ones. You will be asked the spin-only magnetic moment. You will be asked the hybridization. You will be asked the number of ions coming out of a particular complex. So conductance, right? colligative properties, because colligative properties also depend on the number of particles. So like that, there are so many questions that accompany. Once a complex is given, there are so many questions that can be asked. Correct? Next again is from NEET 2024. You are asked the crystal field stabilization energy and the spin-only magnetic moment of Fe F6 3 minus ion respectively. Now Fe F6 is a weak field ligand, and X minus 6 is equal to minus 3, so X is plus 3, and you know that ion is D6S2, so it will be D5 now. So how is the D5? This is 6, means it is octahedral. So T2G is down, EG is up. So you have 5 electrons, and this is weak field ligand, so no pairing. So 1, 2, 3, 4, 5, right? Now this is the barycenter, and then above that is plus 0.6 delta O. Below that is minus 0.4 delta O. What is CFSE? CFSE is number of electrons in the ground and its value. 3 electrons are there in the T2G, and the T2G value is minus 0.4 delta O, and 2 are there in the EG, right? So 2 into, and each one is plus 0.6 delta O. So the total is 0. So crystal field stabilization energy is 0 for this complex. And what about the number of unpaired electrons? There are 5 unpaired electrons. So root of 5 into 5 plus 2, is it not? So 5 into 7, root of 35. Root of 35 is slightly less than 6. So 5 point something. On the other side of 6 it will be. So check. Shall we say crystal field stabilization energy is 0? And then you have 5.9. So option A it is. Clear? So this is another aspect. Finding out of crystal field stabilization energy. Sometimes you'll be asked questions on effective atomic number. So like that, there are so many things. Once a complex is given, so many questions can be asked. The magnetic character also, the stability, so many. Ethylene diamine tetraacetate ion. Tetraacetate, which means that there are 4 minus charges. What is this? Is it hexadentate? Is it ambidentate? Is it monodentate? Is it bidentate? Now, ethylene diamine, let us put ethylene diamine tetraacetic acid. So, CH2, CH2, N, N, CH2, COOH, CH2, COOH, again CH2, COOH, CH2, COOH. Now, if it was in this form, then only 2 nitrogen atoms will donate. So they are the donor atoms. Then it will become a bidentate ligand. But then this is tetraacetate, which means that the hydrogens have been removed. So we'll remove the hydrogens now. So I'll remove this hydrogen, and we'll get a negative charge there. This hydrogen, and we'll put O minus here, O minus, O minus, O minus. So this can also donate, this can donate, this can donate, this can also donate. So there are 6 donor atoms, out of which 2 are nitrogen and 4 are oxygens. So it is a hexadentate ligand. Clear? Option A it is. So ethylene diamine tetraacetate. If it was diacetate, only, so not diacetate, if it was having 2 acetic acids and 2 acetates, that will be having only 2 O minus to donate. So 2 O minus and 2 N will make it tetradentate. So this is not tetradentate, it is hexadentate because there is a 4 minus charge, tetraacetate ion. Now let us look at this. You know that ethylene diamine tetraacetate can be used to remove the, what shall we say, hardness of water. You know that calcium 2 plus and magnesium 2 plus present in hard water can be removed by EDTA. So this is how EDTA encapsulates the Ca2 plus and Mg2 plus. In fact, it can also encapsulate Pb2 plus, and therefore it can be used for treatment of lead poisoning. So EDTA is also used for treatment of lead poisoning as well as in the treatment of hard water to make it soft. Clear? We'll move on now. Now this is again a question from the NEET 2024. Identify the structural features common to this carbonyl and this carbonyl. Now in both these, the metal is joined to the metal. And in both these, the CO are attached at the end. And in both these, the metal is in zero oxidation state. But only in CO8, we have a bridging carbonyl, which is not found in Mn. So A is common, B is common, D is also common, but C is not common. C is there only for the second one, not for the first one. So let us look at the structures that will make it clear. Now, what shall we say is the answer? A, B, and D? That's the option D it is. Now, let us look at the structures. This is the first one, Mn. Now, there is an Mn-Mn bond. There is an Mn-Mn bond. There are terminal CO attached. These are all terminal CO at the end. They're not in the bridge. Between the two Mns, there is no CO. So bridging CO is not there. And all these are having 0 as an overall charge. Carbon monoxide is 0. Therefore, manganese is also 0. Clear? So some more details are provided here. You can check. And then this one. Now we know that you can see here, this and this, if they're lying in the plane, these are not in the plane. And I think this is a better way of looking at. Clear? So one is like this. The other is like this. This is cross. Look at this. This part, how these are arranged and how these are arranged. These are like a cross now. That is like a plus and this is like a cross, isn't it? This is about the first structure. Let us look at the second one. The second one, we have a bridging ligand. CO and CO. These are bridging ligands. Bridging ligands are not found in the previous one. Terminal COs are there, no doubt. This is common. And in all these, cobalt is also in zero oxidation state. Being in zero oxidation state, having a metal-metal bond and having end terminal CO groups is all common. But then bridging ligand is not common. So let us go back to the question now there. Yeah, presence of bridging carbonyl groups is not common to both. Right? Terminal carbonyl groups are metal-metal bond is there. Zero oxidation state is also common. Here. So if you find necessary, you can take a screenshot whenever you find that it will be useful. If you take a screenshot, please do that. Now, again from NEET, this is NEET 2022. There is an assertion and there is a reason. The metal carbon bond in metal carbonyls possesses both sigma and pi character. True. This is what is a synergic bond. Synergic bond will see to it that the metal and carbonyl are holding each other so much so that breaking becomes difficult. So you have a sigma bond, you also have a pi bond. Pi bond will strengthen the sigma bond, and that is what is the synergic bond. So now, if CO has donated very good to the metal can also do very good donation to the CO. But CO to metal bond is sigma, metal to CO bond is pi. So look at this. The ligand to metal bond is pi. No, this is wrong. Just the reverse it is. Metal to ligand is actually pi and Ligand to metal is sigma. So the reason is wrong. So A is correct, but R is not correct. Option D it is. I hope this is clear, and we'll show through illustration how the metal to ligand and ligand to metal bonds are there. All right. Look at this. Now this is a sigma bond, whereas this is a pi bond. From the filled metal T to G, the donation is happening to the empty pi star of the ligand through a pi bond. It's a pi bonding. Whereas sigma bonding is from the ligand. This is a ligand. Ligand to the metal is a sigma bond. Clear? Shall we move on to the next question now? Right? Having done so many questions of all different types, right? We had chosen questions from the previous year so that you will not find that these are questions which have not been asked, not appeared in entrance exams, and probably not going to be asked in any future entrance exam. Now, these are all questions that have appeared in the previous entrance exams, and they're also qualified well enough, right, to judge the student's knowledge. Which complex compound is the most stable? Now, options we need to look at. Now, so many options are there. All these things have a common cobalt. So first thing, we'll notice that. What is the second thing that you'll notice? You'll notice the oxidation state. If you check, all the oxidation states in cobalt are of +3. You can check. NO3 is 1-, so in the B bit, there is no charge. It is 0 because the 3- of NO3 has been cancelled by the 3+ of cobalt. So like that, each of these examples is having an oxidation state of +3 for cobalt. Now, let us look at that. So in this combination, there is NH3, there is H2O, there is Br. Br and H2O are weak field ligands. Strong field ligands are 4 in number. Whereas in B bit, there are 3 NH3s and 3 NO3s. In C, you have an encapsulating ligand 2 in number. So that En is going to make a chelate with cobalt. So En is what? CH2, CH2, NH2, NH2. Just like oxalate, it can also encapsulate. So it can form a chelate. A closed ring can be formed with the central metal. And we said that entropy is the one that is going to favor this, right? And that is going to make delta G negative. And that is what is going to make the process spontaneous, isn't it? And stable. Spontaneous process is the one that gives you a stable substance at the end, isn't it? So it is option C, which you have already seen here, right? So with the push of a button, the answer has appeared much before the explanation happened, right? Sorry for that. This is from NEET 2023. Next question is again statement 1, statement 2. Statements, whether both are correct, one is correct, one is wrong, or both are false, all these things. A homoleptic octahedral complex. Homoleptic means only one ligand. So it is like ML6. Octahedral is an octahedron, right? You'll have a metal here, ligand, 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 and then a ligand there. Forming using a monodentate ligand, a ligand which forms only one bond, will not show stereoisomerism. Yes, there is no geometric, there is no optical, because all are the same ligands. Which do you say is cis and which do you say is trans? All are alike. When you have alike ligands, you will not have any geometrical isomerism. And there is a plane of symmetry. When there is a plane of symmetry, there is no optical isomerism. Clear? So statement 1 is true. So does not show stereoisomerism is correct. Next statement, cis and trans platin are heteroleptic. Yes, they are heteroleptic because they contain ammonia and chlorine, but then they do not belong to palladium, they belong to platinum. So Pt with NH3 taken twice and then Cl2. You know that cisplatin is an anti-cancer drug, right? Transplatin has no activity, but this is belonging to platinum, not belonging to palladium. So this is a wrong statement. Statement 1 is true, statement 2 is wrong. Therefore, option A. Clear? So nothing much to explain here. Shall we move on to the next question? The number of unpaired electrons responsible for the paramagnetic nature of the following complex species are respectively. Now let us look at the options. Options are there. Good. Now all these are octahedral. Yes, check that part. Octahedral, 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 because there are 6 ligands, 6 monodentate ligands. Now Cn is a strong field ligand. So but just before that, we'll write what are the oxidation states. Fe is in +3 oxidation state, the first one. Again, Fe is in +3 oxidation state, the second one. Cobalt is also in +3 oxidation state, and Mn is also in the +3 oxidation state. Now Fe is what? Fe is D6S2. We'll write it here. Cobalt is D7S2. And then manganese is D5S2. Now Fe in +3 will make a D5 configuration. Then cobalt in +3 will make D6. Then you have, this is Fe in +3 state. So this is again D5, Both are D5. So both are Fe in +3 oxidation state. Cobalt is in +3 with D6. Manganese is D5S2. So remove 3 electrons. So it will become D4. Now put the T2G. 1, 2, 3. 1, 2, 3. EG. 1, 2, 3. T2G. And then EG. And the fourth one, I'm putting it here. Yeah. So now, once you have put the T2G and EG, the second thing to note is whether the ligand is strong or weak. Now D5 it is, and it is a strong field ligand. So strong field ligand I'll write here. So 1, 2, 3, pairing has to happen, 4, 5. So how many unpaired electrons? 1 unpaired electron for the first one. Now the second one is a weak field ligand. Again it is D5. So 1, 2, 3, 4, 5. 5 unpaired electrons. So this is 1 unpaired electron. That is 5 unpaired electron. Move on to the third one. F is again a weak field ligand. And is D6. 1, 2, 3, 4, 5, 6. So how many? 4 unpaired electrons. 1, 2, 3, and 4. Then manganese is with a strong field ligand, Cn. Manganese is what? D4. So 1, 2, 3, and then do the pairing. So there are 2 unpaired electrons. So 1, 5, 4, and then 2 is there in option A. I hope this is clear. Understood? Option A. Now the speed can come only when you have practiced well. That is the basic thing that any student needs to be told, right? And probably every student knows it, right? But probably may or may not have put that into practice. But then the basic thing is, unless you have practiced sufficient questions, you will not have the speed. And unless you have the speed and the precision is also important. Precision and even accuracy. Accuracy is the most important one, right? So that will happen only when you have practiced well. You will be in a better position to note what is the answer even before doing all these things. All these things are only for the sake of showing the complete activity. But then a student may bypass all these things and get the answer and then say that A is the answer immediately, right? That will happen only with practice. This every student knows. This every student should put into practice. All right. Now X is the number of acidic oxides among all these things. Now we need to know what are all these things, right? VO2 is amphoteric. V2O3 is amphoteric. This is acidic. V2O5 is also amphoteric, right? And then Mn2O7 is acidic. Now acidic oxides are how many now? Only 2. We have identified as CrO3 and then Mn2O7. Remaining all are amphoteric. Now what is the primary valency of cobalt? That is oxidation state. Oxidation state of cobalt is 3. Is it not? Look at this. This entire thing is 0 valency. And that cobalt X into 2. So 2X is equal to minus of 3 into minus 2. So 2x is 6. So x is equal to plus 3. So 3. The value of x plus 5 is option D. Clear? Option D. It's a different type of question. So any type of question can come. And our idea is to make sure that you get to know as many different questions as possible so that when you actually write the entrance exam, the question is not looking new. So you'll not be taken by surprise. Clear? Next question. An octahedral complex having the molecular composition has 2 isomers of A and B. The solution of A gives a white PPT with AgNO3 and a solution of B gives a white PPT with barium chloride. See, there is a chlorine and there is a sulfate, chloride and a sulfate. You know that chloride is responsible for the white PPT, that is AgCl. And what is responsible for the white PPT in the second solution? That is barium sulfate. So the first one needs to have a Cl outside. The second one needs to have a sulfate outside because only this will become ionizable. So the moment these are broken down, this can take up the Ag plus to form AgCl, which is white PPT. This can take up the Ba2 plus to form BaSO4, which is also white PPT. So in one complex, Cl is outside. In the other complex, sulfate is outside, which means that there is an ionization isomerism, is it not? So it is nothing but ionization isomerism, where you can put it like this: CO NH3 taken 5 times, Cl2 . Now this cobalt is in +3 oxidation state. This is -2, right? So you may require 2 of that, right? And we found one previous example there. So if this was 1 plus, you may require 2 of this, right? Or you may have the sulfate inside. I'm just showing for illustration. A sulfate may be inside, right? And you may have a Cl outside, possible. So this entire thing is going to give a PPT with AgNO3. This will give a PPT with barium chloride. Clear? So those two are ionization isomers. Ionization isomers they are. Clear? Option B it is. Next question. X is the number of electrons in T2G orbitals of the most stable complex ion among all these things. Most stable is this, chelated. Correct? You know that chlorine is not a good field ligand. It's not a strong field ligand. H2 is not a strong field ligand. NH3 is a strong field ligand, no doubt. But then NH3 doesn't encapsulate. It doesn't give a chelate. But then this is a bidentate ligand. It will form a chelate. Now, the nature of the oxide of vanadium of the type V2O6X is, what is the number of unpaired electrons in the most stable complex? The most stable complex ion is in what oxidation state? +3. So there is a T2G down and an EG up, right? So D5 it is, correct? +3 means what? D5. So 1, 2, 3, 4 and then 5. Clear? How many T2G electrons are there? There are 5 electrons. So X is equal to 5. So it is V2O5. V2O5 is what? V2O5 is amphoteric. So it is option A. V2O5 is amphoteric. In fact, V2O3 is also amphoteric. So what we find is that since X is 5, V2O5 is a oxide, but that is amphoteric in character. Next, how did we ask for this? Let us check that because it's a strong field ligand. Stable complex means strong field ligand. Strong field ligand will see to it that the pairing happens. When the pairing happens, all the 5 electrons are there in the T2G. So T2G electrons are how many then? X is equal to 5. Clear? Next question from JEE Main, April 2025. You know that JEE Main happens twice in a year. NEET happens only once in a year. And this happens twice in a year. So this has been taken from April 2025. The correct order of these complex species based on the number of unpaired electrons is. Okay. Now take the first one. First one is Fe in +3 oxidation state. We'll write it here. Cobalt is also in +3 oxidation state. I hope this is not required once again to show how it is +3 and all. We have already shown nickel is in 0 oxidation state, and here nickel is in +2 oxidation state. So this is what D5. Fe3+ means D5. Cobalt +3 means D6. Nickel is, this is D10, because we have seen that carbon monoxide, being a strong field ligand, will push the S electrons into the D, and then D8 S2 will become D10, and this is what, this is D8. Clear? Now let us book the first one. All these are, this is octahedral, this is tetrahedral, and this is square planar. Those things we need to add up to our answering here. So Fe, T2G down, Eg up, weak field ligand, and then D5. So 1, 2, 3, 4, and then 5. Second one, cobalt is in what oxidation state? +3, so it is D6. But then again, weak field ligand again. 4, 5, and then 6. The second one I put. Now nickel tetracarbonyl is actually what? It's a strong field ligand, right? And it is D10. And the last one is a square planar one. 1, 2, 3, 4, 5. D8 it is. So 1, 2, 3, 4, 5, 6, 7, and 8. So this is strong field ligand, no doubt. It is square planar. This is tetrahedral, octahedral. Now how many unpaired electrons are there? 5 are there. Here 4 are there. Here no unpaired electrons. Here also no unpaired electrons. 0 and 0. So it means that this should be the one where both are made equal. No unpaired electrons. And then Fe has got 5 is better than 4. So option C it is. Here. So we have taken up the help of the geometry, whether it is octahedral or tetrahedral or square planar, then the oxidation state, then the number of electrons, and whether it is a strong field ligand or a weak field ligand. All these things only put together can give us the answer. Hope this is clear. Yes. Next question, again from JEE Main, Jan 2025. The condition and consequence that favors T2G3 Eg1. So T2G is given, Eg is there. So 1, 2, and 3. The fourth one has gone up. Why it has gone up? Because it was a weak field ligand. Correct? Because it was a weak field ligand, pairing was not taking place. So delta O was less than pairing. So you get a high spin complex here, more spin complex. So you read a weak field ligand. And what is the consequence? High spin complex. Weak field ligand, high spin complex. There are 4 unpaired electrons. So root of 4 into 4 plus 2. So the spin only magnetic moment will rise up so much, right? So it is a high spin. High spin means more BM, more spin only magnetic moment or more paramagnetic moment. Clear? Option C it is. I hope this is clear. Simple question only. Next, which of the following complexes will have delta O0 and mu as 5.96? So you need to get unpaired electrons 5 in number. And then the CFSE has to be made 0. So equal number of, or the positive Eg and the negative delta T2G, positive Eg and negative T2G should match. Look at the first one. Iron is in +2 oxidation state, so this is D6. Manganese is in, manganese is +2, so it is D5. CO is in D6 because it is removal of 3 electrons. And again, iron is in D6. Now look at the first one. 1, 2, 3, 4, 5, 6 electrons. 1, 2, 3, 4, 5, 6. So this is 4 into minus 0.4, and that one is 2 into plus 0.6. Are they matching? This is 1.2. This is minus 1.6 out. So A is not correct. Look at the second one. Second one I'm putting it here. 1, 2, 3, 4, 5. 1 is SCN is a weak field ligand. NCS is a strong field ligand again. 4 and 5. So this is 2 into plus 0.6. This is 3 into minus 0.4. Here it will match. Here it will be 0. And see how many unpaired electrons are there? 5 unpaired electrons are there. That will give you 5.96, correct? So option is B. It cannot be C because in C, all the electrons are down. 1, 2, 3, 4, 5, 6 because it is weak field. It's a strong field ligand. Strong field ligand will pair up. So you'll have what? 6 into minus 0.4, minus 2.4, maximum negative. So maximum stabilization will happen for the C bit. In the D bit again, D6 it is. So D6 is 1, 2, 3, 4, 5. So 1, 2, 3, you'll pair up 4, 5 and 6. So this is also going to give minus 2.4 delta O. Probably this delta O is more than the delta O coming from ammonia. So, but then the charge is also there. Charge also has to be seen because cobalt is in +3 oxidation state, but iron is in +2 oxidation state. You cannot really make a comparison there. So it is option B. Hope this is clear. Yes, the one that gives CFSE 0 will have the negative of T2G equal to positive of EG, so that they'll cancel out. And there are 5 unpaired electrons. 5 unpaired electrons are found only in B. And SCN minus is a weak field ligand. NCS is a strong field ligand again. Clear? Now, a question coming from the colligative properties, right? This can exist as a complex. 0.1 molar aqueous solution of this complex shows a depression of 0.558. So delta TF is 0.558. Assuming 100% ionization, which means that alpha is equal to 1. So I is equal to N, number of particles, right? Now we'll have to find out which is the complex. Now let us look at the formula. Delta TF equals to I into KF into M. So I is equal to delta TF, which is 0.558 by KF given as 1.86 into molality is 0.1. So this is 0.558 by 0.186. 18 threes are 54. So comes close to 3. So 3 particles after ionization. So I is equal to N. So which one? The first one will give you 1 square bracket and 2 Cl minus. The second one will give you 1 square bracket and 1 Cl minus. The third one give you 1 square bracket and 3 Cl minus. This is giving none. So option A it is. I hope this is clear. Few more questions we'll take up, right? Identify the diamagnetic octahedral complex from below. Diamagnetic. All these are octahedral? Yes. 6 ligands. All are octahedral. Now, it should be diamagnetic. So this is what, this is D. Mn is what? D5S2. So this is D4. This is D6. This is D6 again. This is again D6 because it is +3. Now this is weak field ligand. So forget about this. So this will be out. And look at the first one. Diamagnetic octahedral complex. So 1, 2, 3, 4, 5. It's a D4. 1, 2, 3, 4. 2 unpaired electrons are there. So out. A is out. Now look at the B bit. B bit is D6. 1, 2, 3, 4, 5. And NH3 is a strong field ligand. So 1, 2, 3, 4, 5, and 6. So diamagnetic. What about the C bit? C bit is also D6. So again, that will give you a diamagnetic because Cn- is also a strong field ligand. So this is also diamagnetic. So B and C are diamagnetic. Options. Option A it is. Clear? B and C are diamagnetic. And the last one is paramagnetic because F is a weak field ligand. Whenever you get a weak field ligand, it is going to be paramagnetic. Spin with more value, high spin, will be D. Next, the correct order of the complexes in terms of the wavelength absorbed. Again, wavelength. So again, wavelength means wherever the delta O is less, the wavelength is more. Now let us look at this. Now, which is the strongest? C is the strongest. Clear? So she should be the least. So delta O is maximum for C. Therefore, lambda is minimum. Check for yourself whether option B is correct. Yes. C is the minimum. And D is the maximum because here, look at this. There is a water and there is a chlorine here. Chlorine is a weaker field ligand than water. Therefore, D has to be the maximum. Here, we said wave number will just go the opposite. The type of hybridization and magnetic property of MnCl6 3-, right? So this is actually Mn in +3 oxidation state. Mn is what? D5s2. So this D4. 3 electrons removed from D5s2 will be D4. Now, this is octahedral. So first put the T2G. D4, 1, 2, 3, and then 4. Because there is a weak field ligand, will not do a pairing. So the electron is up. So you cannot have D2sp3. Inner d orbital is not formed because there is only one d orbital empty. And for D2sp3, we need 2 d orbitals to be empty. So this is not possible. So instead of taking the 3d, it will take the 4d, means outer d. So it's an outer orbital. So it will be sp3d2. So it cannot be B, it cannot be D. And then check how many unpaired electrons are there. There are 4 unpaired electrons. So sp3d2 with 4 unpaired electrons. Option A it is. It is not 2 unpaired electrons. It is 4. So option A it is. Hope this is clear. We'll move on further. The d orbital configuration of the complex among all these things that has the highest. So it is so clear. It has to be this. Because T2G6 means what? 6 into minus 0.4 delta O, which is minus 2.4 delta O. This will happen for this, right? In fact, he is not asking that. He is asking what is the configuration. So the configuration will be only for A because A will have the maximum negative delta O, which is the maximum stable complex. Here, option A it is. Next, there are 2 statements here. Again, this is from April 2025, this year. In octahedral complexes, when delta O is less than pairing, high spin complexes are formed. Correct? Yes. When delta O is less than P, low spin complexes are formed. So high spin complexes are not formed. See here. Delta O is less than pairing, means the gap is less. When the gap is less, the electron will not get paired up. So high spin complexes, delta O is less than pairing. Means pairing cannot happen. And when pairing cannot happen, you're going to have low spin complexes. Just let me check if this can be lifted. High spin complexes are formed. Wait. When delta O is less than P, when delta O is, what is this? Both are same. Octahedral complexes, delta O is less than P, high spin complexes are formed. There's some miss here. In tetrahedral complexes, because delta T is less than P, low spin complexes are rarely formed. So you will not get low spin complexes. Let us look at the option. Probably there is some miss here. Yeah. So what does this mean? One of these should be, see, both cannot be same, no? You cannot form high spin complexes as well as low spin complex, isn't it? So somewhere there is a miss here. Look at this. 1, 2, 3, 4, 5. I'll put more gap, less gap. So here the delta O is more than pairing. Here the delta O is less than pairing. So this is a strong field ligand. This is a weak field ligand. This will give a low spin complex. That will give a high spin complex. Now check. When delta O is less than P, high spin complexes are formed. Correct. The first part is correct. When delta O is greater than P, low spin complexes are formed. So just make the small change there. So statement 1 is also true because statement 1 is true. Statement 2 is true is the option that is giving. The option says that it is D, which is correct. So in tetrahedral complexes, the pairing will not happen. Low spin complexes are rarely formed. You will not get a place where pairing happens. So getting low spin is very rare. So you will always have electron entering the upper orbital. So E down, T2 up. So 1, 2, the third will be there, not down. That is in a tetrahedral. That is the T, T2, right? 1, this will be E2. So it will be like this. So you'll find that the pairing will not take place in tetrahedral complex because delta T is less. You know, the delta T is how much of delta O? 4 by 9 of delta O, is it not? Next, this has come out in, so probably this will be the last for this session. JEE Main, Jan 2025, it has come. Now this is potassium 3 plus, therefore this complex is 3 minus, therefore this is plus 3. So this is ferric. This is plus 4, therefore the complex is 4 minus, therefore Fe is 2 plus. So this is D5 configuration, this is D6 configuration. Fe in 2 plus is D6 because Fe is what? D6S2. 2 plus means 2 electrons removed, so it is D6. 3 plus means 3 electrons removed. 1 from D is also removed apart from the 2s, so it will become D5. So 1, 2, 3. Again it is octahedral because 6 and 6. So T2G down, EG up. Now 5 and OH is a weak field ligand. So 1, 2, 3, 4, 5. Don't do the pairing. This is 1, 2, 3, 4, 5 and then 6th one. So here 4 unpaired electrons and here 5 unpaired electrons. So root of 5 into 5 plus 2 here, and that will be there 4 into 4 plus 2 under root. More magnetons. So which one? The first one is 5 point something. So option C it will be. Clear? One last probably. Yeah, this has come out in Jan 2025, JEE Main. Facial meridional isomerism will happen in an octahedral complex. In an octahedral complex, the central metal is here, the ligand down. These are all the ligands, 6 ligands are there. So if you have facial means a ligand L1, 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 this will make a face. This is one face. And then the L2 and L2 and L2 are here. So this is given by M L1 taken 3 times, L2 taken 3 times. So Ma3B3 type. Where it is? Option B it is. This is facial. The meridional will be making a T shape. Look at this. Metal there, central metal, L1, L1, L1. Are you getting a T shape? L2, L2, L2. So L2 with the metal is T shape. So this is meridional. So this will happen only in this type of complexes, right? So I hope you had sufficient experience taking up all different types of questions. right? For want of time, we are probably, ending this session. So we'll conclude this session. I hope you have got sufficient questions to take up, and I hope you will find, right, all these things useful for your entrance exams and also for your board exams, entrance exam of any type, board exam also included. So with this, we'll end the session. Thank you.